Thank you for your introduction. So I'm Lionel Petit from the Laboratory of Physics and Chemistry of Nanobject in Toulouse, in France. And I will talk about magnetometry and graphene Hall sensors. So today, a lot of magnetic nanoobjects deserve to be characterized as individually as possible. This is the case of magnetic nanoparticles, but also of the new 2D van der Waals magnetic material. And to do so, we need sensors that are both sensitive and small enough. And a few years ago, people managed to make this kind of measurement with Hall sensors from epitaxial growth heterojunction structures. But it was at low temperature. But today, with the rise of graphene, we expect to be able to make the same kind of measurement, but up to room temperature. And very recently, one team managed to measure the properties of a 2D van der Waals magnetic material thanks to a graphene Hall sensor. So my job is to make the same kind of measurement with graphene Hall sensors and to optimize the measurement condition through simulations. So first, graphene is the first of the 2D van der Waals material. It's 3.3 angstrom thick, and because of its thickness, we are able to tune the number of carriers in it by applying a gate voltage. I will try to, yes, here you can see a typical Hall device, graphene device, yes, and graphene will act as a plate of a capacitor, where the dielectric medium is the silicon oxide just below. But the most striking feature of graphene is its band structure. Here you can see the conduction band and the valence band touch each other at this point called Dirac cones. Here we have both electron and holes, and you can remark that the bands are linear. And this linearity involves an unconventional density of states that leads to very low carrier density and very high carrier mobility. And these points are crucial for Hall effect. Hall effect is a galvanomagnetic effect that appears when a current flows in a material placed in magnetic field. And here, because of Lorentz force, a transverse voltage will develop, which is called the Hall voltage. And in the diffusive regime, which is the most common one, we can define the conductivity and resistivity tensors that takes these forms in the simplest case when we only consider one kind of carrier. And from that, we can relate the Hall voltage to the magnetic field and to the bias. The bias can be current, voltage, or power. And the link between everything is this normalized sensitivity. And to increase this normalized sensitivity, we need to decrease n, which is the number of carrier, or increase mi, which is the carrier mobility. And that's why graphene is the best material for that. Here you can see a comparison between different technologies. And encapsulated graphene, I mean clean graphene, surpass the best epitaxial growth heterojunction structure by a factor of 2 in terms of sensitivity. But Hall effect in graphene is more complicated than the previous model, because we have to take into account both electron and holes. And it is what we call the two-channel model. And here are the main components of the resistivity tensor. And from that, we can plot the evolution of the main resistances as a function of the gate voltage, I mean, as a function of the doping. So here you can see the blue curve it's the longitudinal resistance, and it's a Lorentzian, which is typical of graphene, and its maximum corresponds to what we call the charge neutrality point. It corresponds to a point where the Fermi level lies exactly at the tip of the Dirac cones. If now I switch to the green curve, which is the all resistance, we can see that graphene is evenly doped. We retrieve the 1/n behavior, which is typical of the sensitivity, because all resistance is just proportional to the sensitivity. But in between, it's more complicated, and it is due to the ambipolar the behavior of graphene. And to increase the oil resistance, we need to decrease this N0, which is the residual charge density due to both temperature and impurities. So we need very clean graphene. From this same model, we developed a more complex one. It's an FEM model that allows every parameter to depend on position. And among the effects that our model can reproduce, I will talk about the linearity of magnetometry resistance. Because if you conduct experiments, you can see that at a certain point, the longitudinal resistance is linear versus the magnetic field. And if we simply take the two-channel model that I presented previously, we cannot have this linear behavior. But with our model, we are able to apply a gate voltage, which is position dependent. And if we add simply a random position dependent gate voltage, we can retrieve this linear behavior. And it has a physical meaning because when graphene is low doped, it is strongly influenced by its environment. And due to that, we do not have a uniform doping of electron and holes, but we have puddles of electron and holes. But sometimes when we have very clean sensor, we are not in the diffusive regime that I talked about previously, but we enter in another regime, which is called the ballistic regime. And here we have to use another model, which is the Binneker model that uses the Landauer-Büttiker formula. The Landauer-Büttiker formula is presented here, and the key point of this model is this TGI coefficient. It's a transmission coefficient from one lead to another. And the brilliant idea of Binneker was to determine this TGI coefficient by Monte Carlo simulation, by determining the trajectories of semi-classical charges using this formula. And from that, we can plot again the main resistances as a function of the gate voltage. And you can see that it's close to the curve that I presented previously. But this similarity only holds because we are under uniform magnetic field. But most of the time, when we want to make magnetometry on a nano object, we have to deal with a non-uniform magnetic field. And that's why I made a lot of simulation in both diffusive and ballistic regime. And I simulated all cross, and I displaced a dipole on top of this all cross to see where to put it to have a good signal. And for every position, I recorded the resistances between this state and this state. It is what I will call the flip signal at remanence. And I did that for different dipole orientation and dipole position. And here are the results for a dipole along the z-axis. In diffusive regime, we have this kind of maps. And these different maps correspond to different wiring configuration. Here you have the typical hole configuration. Here you have the bend configuration. And here the longitudinal one. You can see that in longitudinal configuration, we do not have any signal. And it is because of the parity of longitudinal resistance versus B. But if we switch to ballistic regime, we win one order of magnitude in terms of signal amplitude, which is really cool. But everything will depend strongly on the position of the dipole. So now we have this in mind. We can choose an area with high sensitivity, for example, and And instead of placing a standard dipole, we can simulate with a true nanoobject, such as a 30 nanometer iron nanoparticle. So we simulated that. It's magnetized along the x-axis with a magnetic field along x-axis too. So we did that on OOMF, and from that we can extract cartography that we plugged into our ballistic model. And with that, we can retrieve the cycle of the nanoparticle. So it means that this kind of measurement can give access to the shape of the cycle, to coercitive fields, to magnetization at permanence. So it's very promising way to measure a nanoobject, an individual nanoobject. In parallel of this simulation, I also build my own devices. I do that from exfoliated materials that I can stack using the hot pickup technique. Then I can etch the stack and contact it. And for now, my best Hall sensor exhibits a sensitivity up to 3000 ampere Tesla, which is lower than the best one, but which is higher than the best epitaxial growth heterojunction structures. To conclude, I will continue to make more simulation, especially with offset in magnetic field to simulate out-of-plane cycles, because I expect that some areas will not be sensitive. I will try to increase the quality of my devices, for example, by annealing them to remove this kind of blisters that you can see here. I can prepare more complex van der Waals structure, such as this one. Here you can see the encapsulated graphene is shielded by fuel layer graphene to protect it from parasitic electric fields. Some people manage to reach up to 8000 ampere Tesla, which is this kind of structures. And finally, I will try to deposit and characterize nanoobjects. Thank you for your attention. If you have any question, please ask. I will try to answer it.
Thank you, Lionel. Thank you for your interesting question. So, thank you for your interesting talk. And if there are any questions, please write them in the chat. There's a question from Gunashil, and the question is, would you know how these sensors compare to measurements such as MFM, NV magnetometry, or field sensors that use MTJs?
Yes, the NV center are very promising way to characterize nanoobjects, but it's very hard to use, and it involves very complex physics, and my goal is to propose a way to characterize nanoobjects that everyone can do in his lab, because we do not use very complex things, because we just have to exfoliate materials and stack them. Then we have a device easy to use. And for the case of MFM, from what I know of MFM, we do not have access to. We have access to the force, so it's a derivative of the second derivative of magnetic field, but we cannot have access to the real value of the magnetic field. I think no.
Yeah. Okay. Thank you. And there's one more question. What is your main limitation in terms of science and performance?
I think the both are linked, because the smaller are my devices, the higher is my signal. And for now, I cannot reach crosses smaller than 200 nanometer because it will destroy the mobility of my carriers because you will have a lot of diffusion on the edges of my devices. So it's a trade-off between quality of my device and size of my device. So.
Okay, thank you, Lionel. But what is the actual sensitivity? Can we use these sensors for detecting, for example, electromagnetic field of biological objects?
So the sensitivity now is around 3,000 ampere Tesla, but this 3,000 ampere Tesla is just defined under uniform magnetic field. And if you plan to use this kind of sensor to characterize small bio nano objects, it's more complicated because it will depend